I'm Marcus Rakel. I'm at Washington University in St. Louis. I'm a neurologist by training, but most of my work has been done in the laboratories of the Mallinckrodt Institute of Radiology. No, emphatically not. No, this is, you still hear this, or I'm only using part of my brain, or I activated my brain, or I turned it on, and all of which implies that it goes into some sort of dormant state that if I were to look in, it would just be a true black box, and nothing could be further from the truth. The first thing to know is that among the organs of the body, it's continuously the most expensive. Now, the muscles can have bursts of energy use when you're running or walking, but they can go to zero. The brain kind of oscillates somewhere between 95% and 100% most of the time. And we've known this for a long time. It goes back to studies that were done right after the Second World War, where whole brain metabolism was measured, the amount of oxygen consumed, which tells us how much energy is used, and it became patently obvious that it was using a lot. It's only 2% of the body's weight, and it's 20% of the cost of running the body. That's in an adult. In a child of age 10, it is twice the cost. One of the clever things we learned to do when imaging was developed was to be able to compare doing something to not doing something. And we got rather clever of being able to take your brain and my brain, and we could, with computers, make them sit one on top of the other so we could add them all up. And we could compare you sitting there and moving your hand or looking at a flashing light or something, and we looked at the difference. And so when you looked at many of those images, and now with fMRI you do much of the same thing, and you see a spot lighting up here and a spot lighting up here, and depending on what the color scale is you use, my gosh, it looks like this thing just lit up and there's nothing in the background. Well, the thing is, you've just subtracted the background. And if you actually get in there and measure the amount of change, it's inside 10%. What you can learn from this is that all of the large scale systems, your somatomotor system, your dorsal and ventral attention system, your visual system, your auditory system, the basal ganglia, they're all conspiring in this sort of thing in such a way that you can lay out a map of the basic functional structure of a human brain or a non-human primate or a cat or a rat or a mouse. This you can find the default mode network all the way down to a mouse now in one form, in an abbreviated form, but the same general thing is there. My usual answer to a question in one sentence, what is the brain doing? It's in the prediction business. It has built a model of the world, and it applies that model to understanding what we see and hear and touch. It's for sure that. And the other side of that coin is Vernon Mountcastle said in a fabulous lecture he gave before he died at Hopkins, that our view of the world is an illusion. That most of what we see in the world, whether it's you and these screens and the gentleman behind the camera here, is being constructed by my brain because of the very impoverished data that actually gets through my eyes and into my visual cortex. It is a fraction of what's out there. And it's so counterintuitive. It just as if oh, this can't be true, but it is. And so how does this work? Well, the brain has to be in the prediction business. And of course that makes complete sense. As James and various other people have talked about this, how in the devil would you get out of bed and get dressed in the morning if you hadn't already programmed this? I mean, really, you don't think as you're sitting there, and if you write or you do whatever you do, you're not thinking about the detailed muscles and how you're moving, all this stuff. Of course not. It's all been laid out. I think a lot about what its role is, but I think the bigger picture that has emerged out of it is to try to better understand the organization of the brain that is ongoing, intrinsic, non-conscious, which is something we haven't talked about, but most of what it's doing is not conscious. Getting a better understanding of how that is organized, and this involves not only at the very large scale of a neuroimaging device, but electrophysiologically and metabolically and all of these sorts of things. How does this come about? How does a piece of biology get itself organized? My name is Marcus Rakel, and I'm a neuroscientist.